the last lesson.
Yeah, so we are going to end with a bang. This is a cool lesson, all right? This is a cool lesson because if you think about what we've been doing, is creating objects where all of them had a circular cross-section because we were revolving it around one of the axes. So if we would have sliced it perpendicular to the axis, it would have come out as a perfect circle every time. Now that circle would have varied in radius, that's why we had to integrate the function, okay? But we were dealing with things that had a circular cross-section. Well, this lesson is all about things that don't have a circular cross-section. In fact, one good example that we see in nature here is the star fruit, okay? This is a pretty cool one because this star fruit, if you slice it anywhere, you get a star as long as you slice it perpendicular to its length, you know? You get this little star, and if you cut it closer to the end, obviously it's going to be smaller, but it'll still be the same cross-section, the same shape, all right? And that's what's kind of cool about this. That's why I put that picture there, because that'll help you kind of visualize some of the things we're working with, okay? But let's look at this right here. We have a little bit different perspective on our axis. Notice that X is down kind of at an angle there, and Y is coming out towards our right there. They're both, and this object is sitting on top of them, okay? Now, when you see this, it's important to pay attention to the fact of what's labeled, okay? So that's our Y, our positive Y-axis, which means back here in the background is the negative Y. This would be our positive X, and then back here going that way would be our negative X. All right, so that's going to be important as you determine bounds and also determine. We're going to have to deal with higher and lower functions because we're going to work with area between, okay? But here what we have is a cross-section, in this case, that's perpendicular to the x-axis, okay? Notice here's our x-axis going through this way. We've done our cross-section perpendicular to that. If we have a three-dimensional object that's constructed in this way, the volume of that is going to be the integral from a to b of the area of x dx. That a of x is the area of our cross-section, but recognize that depending on what x value you're using, that cross-section is going to be different size. Okay, so for example, here's a delta x when x is here, and if I go this way, notice the cross-section is actually going to look like this. Okay, so you see it does have the same shape in general here, but it's a much different size because our x value has changed. Okay? Now, our bounds, notice, are going to be values of x. So our a would be back here, and our b would be up here. Okay? So we're integrating from a to b along the x-axis. The challenge of this is going to be finding the expression of area. Okay? It's going to be finding the expression of area. Now, think back to what we said at the beginning. We've been doing solids of revolution. The cross-section was a circle. Formula of a circle is pi r squared. Remember, we were doing v equals the integral from a to b of pi times the function squared. Well, this is area. Okay? So it's actually the same formula, we just have a different shape to work with now. Does that make sense? Okay? Now, this one right here would actually be particularly difficult to do because our cross-section is kind of a weird shape. And we'd have to try to come up with some function of x that would represent that area. Okay?
It's something like a triangle, which is 1/2 pH.
Yeah, kind of, except it's curved,
yeah, but
right?
It's a bit bigger.
Yeah. So what actually ends up happening, and this happens a lot, is in this case, it's actually easier to make our cross sections perpendicular to the y-axis. Okay? And that's what we see right here. Here we have the same shape. Okay? We have that same shape. Here's that front edge. Okay? So it's the same shape, but notice when we make the cross section perpendicular to the y-axis, it ends up being a perfect square. Okay? Now the nice thing is you're going to be told which cross section to use and what that cross section is. Okay, you're going to be told whether this is a square or maybe a rectangle or maybe a semicircle or equilateral triangle. We'll do an example of here in a sec. Okay, but notice now we're doing an integral along y, so we're going to be using y coordinates. And notice here's y equals c to d. Okay, so along the y-axis, we're doing the integral of that. But again, we're just doing the area as a function of y in this case. Okay? Yes?
So, I don't know if they're just making it a perfect square to make it easier, but wouldn't, like, the top part of the square, the front part be lower than the back part? Because, I mean, it's curving on the top, and same thing with the sides. I don't know if that makes sense.
Well, remember what we're doing, okay? And this is, we did this with the disk method. The disk method, and also going all the way back to Riemann sums, yes, when you look at it like this, where we have a little square prism here, yes, that's not going to be perfectly hitting this. But how did we develop our Riemann sums? We did it as this delta y went to 0, as the number of these that we added up approached infinity. So these are becoming infinitely thin. So yes, while as it's drawn here, if I did it to touch both sides, the top would be bigger than the bottom. When they get paper thin, you know, they're the same, okay, as n approaches infinity. So again, this is developed actually the same way our disk method was, and it's the same way our Riemann sums were to develop the concept of an integral in the first place. Okay? Now, here's an example where we have this solid, and this solid is has a base that's bounded by these three lines. Okay, so you notice I kind of color coded it since it's hard to follow some of this when it's drawn in 2 dimensions. Okay, so here kind of in the background we have x equals 0, which is our y-axis. Notice back here this says y, so that's the positive end of the y-axis. Alright, and then down here it says x, so this is the positive side of the x-axis. Alright, so this x equals 0 is one of the sides of the base, and then f of x is 1 minus a half x, is one other side of this triangular base, and negative 1 plus x over 2 is the third side of this triangular base. Okay? So we have that base, and then the way we've actually constructed this is by using the base, we made an equilateral triangle. So every one of these triangles, like the one I've drawn here, has equal sides. Okay? Yeah, Joey?
There's no z-axis, but like there is. Like if we were to draw this like a normal graph, we would just see a triangle. So how would we know what to do?
Yeah, I mean you could draw the z-axis if you want.
I mean, if it was just an xy, we would just see a triangle.
The thing with these is we're going to give you picture to work off of. Obviously, if you were doing this like realistically, you would use some kind of a graphing software probably, or make a physical structure yourself to build these. But for this, the key here though is recognizing that every cross section is an equilateral triangle. You will also be told that part of this. Okay. So let's think about what we're doing here, and let's think about the equilateral triangle specifically. I'm going to actually draw the equilateral triangle, because if I can represent the area of this as a function of x, then I know how to take the integral. To find the volume by taking the integral. Okay? Because remember, the volume is going to be the integral from where to where? We can already tell that.
-1 to 1. Or 0 to 2.
From 0 to 2. Okay, because we're going to go along the x-axis, because our cross sections are perpendicular to the x-axis. So we're going from 0 to 2 of that area function. Okay? So if this is equilateral, let's think this through. This is a side, side, side. Okay, they're all the same. What else do we know about this triangle?
It's 2 90-degree triangles.
Okay, we could make it into 2 90-degree triangles, and that would be the height, right? So actually we know that the area is the side times the height divided by 2. What else do we know?
Well, since it's a 60, 60, 60 originally, you know you have a 30, 60, 90 triangle on the side.
There we go.
Is side times the square root of 3. Or 1/2 side times the square root of 3.
Okay, yeah. So let's look at this a little more closely here. If the whole side is s, then this is a half s, and that means h is 1/2 s times the square root of 3, using that 1, 2 radical 3 pattern for a 30, 60, 90. Okay? So with that being said, now I can rewrite this a little bit. The area is now root 3 over 2 times s over 2. Which obviously would simplify to radical 3s squared over 2. Now, or sorry, over 4. I had a half on top and a half on the bottom. Okay. Now, that, by the way, is the formula for the area of an equilateral triangle. Notice I haven't used anything from the actual problem yet to do that. That is a formula. It might be handy to know. Okay.
It's just 1/2
It is 1/2 base times height, yeah. But we did it with it being an equilateral triangle specifically. It'll end up being radical 3 over 4 s squared.
Because we didn't know the height.
Yeah.
So we should memorize
Okay.
that or no?
You don't have to, no. You can always figure it out. Alright? So at this point, this is where our problem comes in. At this point, we have to figure out what that side is in terms of x. Okay? So going back here, remember f of x was y equals 1 minus x over 2. And g of x was negative 1 plus x over 2. So, how am I going to find how long this side is?
It's the distance between those two at that.
Yeah, it's the distance between those two at that value of x, right? How do you find distance between two things linearly?
Or distance.
Y equals x2 minus x1 squared
we're not doing 2D, it's just one-dimensional. What'd you say?
Just subtract the function.
Just subtract.
Oh, I was overthinking.
Here's that upper minus the lower function. You remember doing that when we did area between? Okay? Now, we're just finding the distance between. So it's going to be, the side is going to equal the upper function minus the lower function. Well, if the positive y is up here, then this is going to be our upper function, and this is going to be the lower function. So I'm doing, the side is f minus g. Okay? Well, that's a 1 minus x over 2 minus a negative 1 plus x over 2. So I have 2 minus 2x over 2, or 2 minus x. Now we have a of x. Because I can now plug that in for s, and I have the function a of x equals radical 3 over 4 times 2 minus x squared.
Wow. We solved
Okay.
the puzzle.
And then all we have to do is actually take the integral. Okay? We have to take the integral. So now we know that this is the integral from 0 to 2 of root 3 over 4 times 2 minus x squared dx. U is 2 minus x, so du negative 1 dx.
Can we pull the square root 3 over 4 out?
We definitely can, and I'm gonna, so it's gonna be negative square root of 3 over 4. I need to put a negative in here and a negative out there, so that's why it's negative root 3 over 4. And then that's times the integral of u squared du. This is where you got to be careful with this one. Okay? Check this out. U was 2 minus x. So when I'm doing my bounds, u is going to equal 2 minus 2 for my upper bound. That's 0. U equals 2 minus 0 for my lower bound, which is 2. So this is actually integrating backwards from 2 to 0, but that's okay because remember there's a negative outside. That'll cancel out the negatives. Works out real nicely for us. Okay? So negative root 3 over 4 times u cubed over 3 evaluated from 2 to 0 is a negative root 3 over 4 times 0 minus 8/3. Negative times negative is a positive. 8 over 4 is 2, so it's 2 root 3 over 3 units cubed.
Should we expect to see us on the free response for next time?
That was an honest question too.
So, here we had equilateral triangles. You had to construct your a of x using the functions you were given and using a formula for the area of equilateral triangles. You might be given semicircles. You might be given a rectangle. In fact,
This is hard to
if you look at your one homework problem, you'll see that. If you look at the one I gave you to practice down here, okay, notice in this case we're finding the volume of the solid whose base is bounded by the graphs of this line and a parabola, okay? And the cross section, notice we could make one of these the cross section where we have squares. And that's going to be those are going to be perpendicular to the x-axis as squares, or instead of squares, we could make them all rectangles that have a height of 1. Okay? Notice I'm making a consistent height so that they're all the same cross section. Okay? So, two different three-dimensional objects, one with squares and one with rectangles.
I just